Let's figure out how to calculate the ratio of two forms of alanine at pH 4. So the first place to start is look up at the amino acid sheet and draw the alanine. And I'm going to draw it, and I recommend you do too, always in fully protonated form. So all amino acids have, why is it not working? All amino acids have NH3 plus group, amino group, CH, C double bond O, OH, carboxyl group, right? And the R group. R group is a side chain. And for alanine, it's just going to be CH3. And then we're going to draw different ionization forms, right? So alanine has two pKa's. Let me change pKa. So pK for carboxyl group, if you look it up in the pKa table, pK is 2.3, and for amino group, it's 9.7. So these pKa's tell us about kind of how well each functional group holds on to the proton that they can give up, right? So from this, we can tell that carboxyl group is going to give up its proton first, NH3 plus, CH, C double bond O, O minus, right? And then here's my side chain. Get rid of this guy. All right, and then that's the first pK. And then the second pK, we're going to lose proton on the amino group. And then amino group will just become NH2, CH, CO, O minus with the side chain, right? So we have three forms of alanine here. And let's label. So the first pK is for 2.3 and the second pK 9.7. At 9.7, that's where the amino group loses the proton, right? And then at 2.3, it's this proton that comes off, leaving behind carboxyl group. All right, so we need some way to refer to these different forms, and let's just name them. Let's see, I'll choose blue light. So this one, what's the net charge on this this form, right? So we have, whoops, where's the pointer here? Okay, I'll just do a highlight. So here we have a positive charge and the no charge. So the net charge is going to be +1 net charge, right? Then the middle group has a positive charge on the amino, negative on the carboxyl. So the net charge is 0. I'm going to call that Zwitter ion. Right, so net charge is 0. And the last one has net charge -1. This would be fully deprotonated form. Deprotonated. Right, so all the protons that could be lost got lost. And the first one, the +1 net charge, will be fully protonated. Okay, and we can refer to it by the net charge. So if our goal is to figure out what's the net charge at pH 4, all we have to do is look at the different forms and figure out where's 4 belong to, right? So 4 is going to be between 2.3 and 9.7. So main form, the most abundant form, is going to be the Zwitter ion form, right? But what's the ratio of the two most abundant forms? Let me get rid of some of these highlights. Okay, so then 4 is closest to pK 2.3, much closer than to 9.7. So that's the pK I'm going to use. So to figure out what's the ratio, right? We need Henderson-Hasselbalch. So ratio is going to come from Henderson-Hasselbalch equation that says pH over buffer equals to pKa plus log of ratio deprotonated form over protonated form. Okay, and so in the in the equilibrium, we're looking at which form is protonated, HA, and which form is deprotonated, right? So since we're working with pK 2.3, for this pKa, HA protonated is the +1 form, and deprotonated A minus, right? So if we were working with the other pKa, it would be the other way, like it would shift. All right, and so to get the ratio, ratio is going to be A minus over HA, right? We just need to rearrange our Henderson-Hasselbalch equation. So I'm just going to continue working with that. So I'll write here log of ratio, A minus over HA, equals to pH minus pKa. And if we plug that in, pH equals to 4.0, pKa is 2.3. That's going to be 1.7. And so now we have that log of ratio. I'll call it x for now. So put x equals. And so how do we get something from under the log, right? So we have log of x. All of our logs that we work with in biochemistry are going to be log base 10 equals 1.7. So that means 10 raised to power 1.7 equals to what's under the log, right? And if we plug that in, we're going to get, let me see, I just did that, like 50.1. 50.1, right? So what does this number mean? It means we have 50 times more A minus deprotonated form, which in this case is Zwitter ion, compared to then HA, which is the net charge plus 1 form. Yeah, so that's how we calculate this. All right, so now do you want to try to do this for, say, pH 8? Could you do the same thing? So pause here, now that you watched it, pause here and do this for what's the two most abundant forms at pH 8, at pH equals to 8. So which form is HA? Which form is A minus? Which pKa are you going to use, right? So pKa. And what's the ratio? So figure out ratio. Okay, so pause here. All right, so if we go back, I'm just gonna keep working on this. If we go back, pH 8 is closest to pKa 9.7, right? And so for that equilibrium, let me maybe switch back to a different color. For this equilibrium, the Zwitter ion is going to act as protonated form because of this proton here on the amino group. And then -1 form will be A minus, right? And the pKa we're working with is 9.7. So I'll put here HA is going to be Zwitter ion, or net charge of 0. The A minus is going to be net charge of -1, deprotonated fully. All protons are gone. The pKa we're working with is 9.7, and the ratio, so I'll put here again, x, A minus over HA, is going to be 10 raised to the power of pH of 8 minus 9.7. So we're doing the same math we did before, pH, right? So it's like right here, pH minus pKa, and then you raise 10 to that power. So it's going to be 10 to the negative 1.7, right? Notice it's very similar to this except negative. And so we end up with ratio of A minus over HA equals 0.0, see, so I don't make a mistake here, 99, also approximately 0.02, which is also happens to be approximately 1 over 50. So we have 50 times more Zwitter ion compared to fully deprotonated form. Okay, so if you're able to do that, I think you've nailed it and you're ready for other problems. Stop recording.